All right, welcome everyone. We're going to get started. So, believe it or not, this is the last week of class already. It seems it seemed like the semester went really fast and really had a lot to it. Um, but last week, so we'll gonna be touching on a few kind of last ideas for the course. Um, Today we're going to be looking at learning outcome IC3. So this will be where we see how to use definite integrals to calculate displacement and total distance traveled for an object that's moving in a straight line. And then kind of generalize that a little bit for net change. So we'll see how to use definite integrals to calculate the net change. So that's learning outcome IC3. We're going to just start probably talking about, if we have time, we'll get to a little bit of IC4, which that'll be our last topic for the course. And what we're going to see there is kind of the definition of definite integral. We'll probably get to that mostly on Thursday, though. So that's kind of the last topics for the course. Reminder, we have our follow-up exam 6 scheduled for Thursday at 6:30. We're finishing up the grading for the exam from last week, so that should be available to you later this afternoon. So make sure you know, take a look at what you got wrong so that you know you can retry those questions on the follow-up exam on Thursday. Also, I'll be opening the homework assignments, so all the old homework assignments, those will be reopened on Thursday and will be open until next Monday. So you have a little bit of time there, a little bit of window to go back and complete any problems that you missed the first time. I will have office hours this week on Wednesday and Friday, 11 to 12. And then I will be having office hours and probably some sort of review session during finals week. So I'll make an announcement about that on the class website. So we will have a review session before the final exam. Our final exam is next Thursday. And so we have the follow-up exam this week where you can retry any of the questions from exams 1 through 6. And then also for the final exam, if you can score a 90% or above on any of the final exam questions, and it's directly related to one of our learning outcome questions, then you can still get a mastery for our recitation exams. So if you can show improvement on that final exam, retroactive, you can go back and get credit for any recitation exam questions that you haven't gotten credit for yet. So it's kind of like your fourth chance on some of these exam questions. So just a reminder about that. All right, so let's get into it for today. So we're gonna see net change, and we'll start off with our definite integral and how we calculate it. So let's say we have the integral from a to b of some function f prime of x. So we're integrating f prime. We know how to calculate that. We find the antiderivative. Antiderivative of f prime is f. And then we plug in our limits of integration and subtract. So f of b minus f of a. Top limit goes in first, bottom limit goes in second, and we subtract. All right, so this is how we calculate definite integrals, but we're going to look at an interpretation of what this formula means. So on the left there, what do we have? Well, we have the integral over our interval a to b of some instantaneous rate of change function. So f prime, go back all the way to the beginning of the semester, f prime, the derivative, describes how our function f is changing at every single instantaneous moment. So what this definite integral is doing is it takes into account all those little instantaneous changes in our function, and it kind of puts them together. And what we get out then is the net change of our original function. So on the right side, f of b minus f of a, that is the net change of the original function f as x varies from a to b. So f of b, we can think of this as the ending value of our function. And f of a is the starting value. And so when we calculate the net change of our function f, we're just looking at, okay, what do we end up with? And let's subtract what we started with and see how much we changed over that interval from a to b. Did we go up? Did we go down? So we're just kind of looking at the net change. How much we ended with minus how much we started with. So that's the right side of this net change formula. On the left side, going back, the integral of f prime, what that's doing is it's saying, let's look at all these tiny little changes, all these instantaneous changes of our function. And that's what f prime is doing, is it's looking at all these tiny little instantaneous changes of f. And let's put them all together and see what happens kind of big picture, what happens overall to our function f. And so the integral here is really describing the cumulative effect on our function f of all those little changes described by f prime. On that interval from a to b. So f prime describes all these tiny little changes at every single little instant, and what the integral does is it puts them all together and says, here's what happened. Here's what you ended with, here's what you started with, and that's it. And so what we're going to see is how this relates to a few examples, and the primary example we'll be looking at is motion in a straight line. So let's kind of look at a possible setup for motion in a straight line. We might be integrating our velocity function over some time interval. And we know velocity, we talked about this a little bit ago, is the derivative of our position function. And so if we were to reframe this net change formula in the context of position and motion in a straight line, the integral of f prime, integral of a derivative, the antiderivative of s prime is just s. We plug the top number in, plug the bottom number in, and we subtract. So we can think of s of b as our ending position at time t equals b. S of a is our starting position at time t equals a. And we're looking at their difference. So when we integrate the velocity function over some time interval, we're really integrating the derivative of our position function over that same time interval. And the antiderivative of s prime is just s. And then we plug the top number in, plug the bottom number in, and subtract. And we can interpret s of b as, we have this object that's moving back and forth. S of b is our ending position. S of a is our starting position. And what their difference, what that subtraction, what that difference actually calculates, we call the displacement. So let's look at a little picture. Let's say we had our straight line here, And let's say this is our object at time t equals a. And what's going to happen is that object's just going to move back and forth on that line. And what displacement measures is, well, how far away are we from where we started, essentially. So here might be our object at time t equals b. And so what displacement is measuring is this distance here. That's our displacement. So displacement can be positive. So if you end up in the positive, if your ending position is in the positive direction, displacement would be negative, or would be positive. If you end up in the negative direction, then displacement would be negative. And if somehow you start and stop at the exact same place, well, then displacement would be 0. So displacement can be positive, negative, or 0. So let's kind of think of this in terms of another example. Let's look at the scenario where we have a reservoir, a tank, and we're filling it up and maybe draining it out with water. So we're going to let function v of t be the volume of water in this reservoir at time t. So let's draw a little picture. So here's our reservoir, and maybe water can come in. So there's a possible place where water can flow in, and maybe there's a drain. So there's a place here where water can flow out. And what v of t is measuring is it's measuring the volume of water in this tank. So if v of t describes the volume, then its derivative v prime describes the change in volume. So if water's flowing in, our volume's going to go up, so v prime would be positive. And if water's draining out, then the volume is going down, so v prime would be negative. So v prime is describing the rate at which water flows into and out of the reservoir at time t. All right, so what would our net change formula look like in this case? Well, it'd be the integral from a to b. A and b would be our time interval of v prime. And we know the antiderivative of v prime is v, so it'd be the volume function. And so we have our antiderivative, top number goes in first, bottom number goes in second, and we subtract. So it'd be the volume at time b minus the volume at time a. So over our time interval, what these values would represent, the volume v of b here would represent our ending water level, or water volume. And v of a would represent our starting volume. And so v of b minus v of a would be the net effect. So how much water came in during that time interval, or how much water essentially flowed out during that time interval. So it'd be just kind of the net change. So we watch our water level, goes up, it might go down, but what is the difference between how much volume we started with versus what we ended with? So v of b minus v of a is just calculating, what the end result is. How much did our volume go up? How much did our volume go down? So that's another way to interpret v prime the integral of v prime is we're looking at all those little changes. So at every single moment of time, water's flowing in, water might be flowing out. And so what the integral does is it looks at all those momentary changes in our volume, puts them all together and says, this is what the net effect is. This is what happened over that entire interval. So let's kind of put this in the context of what we were talking about last Thursday, which is area under the curve. So let's say we have this graph here, and it's the graph of v prime. So this is the graph of the derivative. And we know when we integrate a function, if we're thinking of it in terms of area, the integral is related to the area under the curve. So what does the area for each of these sections represent in terms of the problem here, the context, in terms of volume? So let's look at, we'll start with this first little region here. So maybe let's give these places where v prime crosses the horizontal axis. So maybe let's say this happens at t1, and this one happens over here at time t2. And so if we could calculate the area of that first shaded region, what does that represent? So what would be the kind of interpretation of the area from A to T1? Well, that region's above the horizontal axis. And what that would represent is it would represent the volume that's flowing into our reservoir during that time interval. So the way we would interpret this is that the overall effect of what's happening to our system is that water, the volume of our reservoir is going up during that time. So this would be the volume of water in during this interval. So, or how much our so if we could calculate the area of that shaded region from A to T1, that would tell us how much our water level goes up during that time interval. So the region is above the horizontal axis, so that means V prime is positive, so more water is flowing into our region, or into our reservoir, than is flowing out, so our volume is going up. And so if we could look at the area of that shaded region from A to T1, what we're actually calculating then is how much water, we're calculating the volume of water as the water level rises in our reservoir. Now, if we were to look at the shaded region below, in between T1 and T2, what's happening here is V prime is negative. So when V prime is negative, the volume is going down. So V prime is negative. And so what this represents is if we could calculate the area from T1 to T2, this represents the volume of water how much water do we lose in our reservoir during that time. So the net effect there, when our region, our V prime function is negative, is volume is going down. And so we can interpret the area of that shaded region as being, well, that's how much water do we lose during that time interval. And so finally, we have one more region. This one sits above the horizontal axis. And so here, V prime is positive. So what's happening? Well, water's flowing in, water's flowing out, but the net effect here, if V prime is positive, is that our volume is going up. So our water level goes back up. And so if we could calculate the area of this shaded region, so we're going from T2 to B, if we could calculate the area of that shaded region, what that would represent then is how much water do we gain during that time interval. So this represents the volume of water. And I should say, really the net volume in each of these is the net volume. Because, we might have water. So in this system, we might have water flowing into our tank, and then simultaneously it might be draining out. But when our V prime function is above the horizontal axis, what's happening is our water level is going up. So the water level, the water that's coming in and the water that's draining out of our system, we have more water that's coming in than is going out. So our volume is going up. Now when V prime drops below the horizontal axis, what happens? Well, our water level starts to go down. So we might still have water pumping into our system, but now we have more water that's draining out. And so by looking at the area of each of those shaded regions, if we look at the area from A to T1, really what we're calculating there is the net volume, how much water comes into our system during that interval. When V prime is negative in that section from T1 to T2, if we could calculate the area of that shaded region, really what we're looking at is how much does our water level go down? What is the volume of water that we lose in our system? And if we could integrate from T2 to B, if we could find the area for that shaded region, well, really what we're calculating then is how much does our water level go up? What is the change in that volume? So that's really what we're going to be looking at for a lot of these examples. And this is one for volume. We're primarily going to be looking at displacement and total distance. But this is just another interpretation of that net change formula in the context of volume in a reservoir. So there's other examples. You might look at, say, if you have a chemical reaction, and you might look at, say, the concentration of a chemical during that chemical reaction. So, it might be coming together, might be breaking apart. So you might have kind of more of a certain chemical, and during one section of time, and then that chemical might break apart, so you lose it during another section of time. And so integrating the concentration function, or the derivative of the concentration function, you'd be looking at sort of what the net effect is over a certain time interval. So there's a whole bunch of examples. We looked at volume here. We're primarily going to be looking at displacement and something else, which we'll see next, and it's total distance. So motion in a straight line is where we're going to be primarily focusing here. So let's just recall, V of t describes the velocity of an object that moves in a straight line. And we've already looked at displacement. So displacement measures the distance and direction between the starting position and the ending position of the object. So, as soon as we see that wording direction, we know it could be positive or negative. So for a motion in a straight line, there's really only two directions you can go. You can go one way, which might be the positive direction, or you can go the other way, and that's the negative direction. So you're kind of limited with a straight line. There's only two ways to go. And so what displacement's measuring is the distance between the starting position and the ending position and your direction. Did you move to the right? Did you move to the left? Did you go up? Did you end up going down? And we know how to calculate this. So displacement over a time interval is equal to the integral from a to b of the velocity function. All right. So there might be something else that we're interested in, and that's total distance. So displacement doesn't capture everything. It only tells us, where did we start? Where did we end? What's the distance there? But we might have bounced around a whole bunch, and we might be interested in, well, how far did we travel throughout all of that? So we went up, we went down, we went back up, bounced around. What is the total distance that we traveled? And so how we calculate this is a little bit different. Still related to the integral, and it's still related to the integral of our velocity function. The only difference is we have an absolute value sign. So what the absolute value sign is doing is it's effectively kind of getting rid of the direction in our calculations. So total distance really doesn't have, we're not interested in the direction we're traveling in. We just want to know how far we're traveling. Displacement kind of worries about both. It's worried about the distance you're traveling, but then also the direction that you end up in. So when we think about displacement, we can have positive values, we can have negative values, we can also have a zero value. For total distance, we have to have a positive value or maybe zero. Maybe we don't move at all. But total distance traveled has to be positive. We can't travel negative distance. All right, so let's think of this, each of these integrals in terms of distance. So when we calculate displacement, when we calculate the integral from a to b of our velocity function, the way we can think of this is it's the distance traveled in the positive direction. And let me shorten that up. It's distance in the positive direction. And it's the distance in the negative direction. And we subtract. So what displacement's doing is it's saying, okay, let's figure out how far we traveled going up, how far we traveled going down, and let's just subtract those two values, and that gives us the displacement. Now, total distance, what that does is it takes the distance that we travel in the positive direction, it takes the same, we're interested in the same thing, distance in the negative direction, but now we're not interested in direction. We're only interested in how far we travel, so we just add those two distances together to get the total distance. And so those might look pretty, the setup here might start looking familiar if we think back to our area problem. And calculating the distance traveled in the positive direction, you could think of this as like the area above the curve. And then distance traveled in the negative direction is the area for the region that goes below the horizontal axis. So to get the displacement, we can calculate the area above the x or above the t-axis, calculate the area below the t-axis, and subtract. And then for total distance, what we're doing is we're really looking at those same two areas, but then we just add them together. So it's the area above plus the area below. So when we let's look at this little example here. We have a graph of some velocity function. It looks like a straight line, crosses the t-axis at time c. But what is the implication here for the area of this shaded region? Well, here v prime is, or v is positive. So that means we're traveling in the positive direction. And so the area of this shaded region, this is the area above, and this corresponds to the distance in the positive direction. So looking at the area for that shaded region, if we interpret it in terms of what we're looking at, velocity, the area for that shaded region really is giving us the distance that we travel in the positive direction during that time. And if we look at this section here, where v prime is negative, well, this is the area below the curve, or below the horizontal axis. And what's happening here is when v prime is negative, now we're moving in the other direction. And so by calculating the area of this shaded region, we're really looking at the distance traveled in the negative direction. So it helps to, when we're thinking of velocity and distance traveled, it helps to think of it just in terms of area under the curve. And so, as someone pointed out, nice observation. So really what we're calculating here with displacement, this is the net area. So this is what we looked at back in the last section. We defined net area, which was just area above minus the area below. And we also defined total area. And that's really another way to interpret displacement and total distance. Displacement is just the net area under the velocity curve. Total distance is we could think of that as the total area under the curve and between the x or horizontal axis. Nice. Yeah, so really there's not too much new here. The types of calculations that we're going to be doing, we've done all them already. We're just kind of putting it into a different context of saying, okay, let's say our function now is a velocity function. What does the integral represent? So we've done these sorts of things before. Let's look at this graph a little bit more and kind of see, just to get some feel for how these calculations work. Let's just describe how this object is moving if this were its graph. So let's say we have a vertical line. So this is the line that our object is going to move in, up and down. And let's say the positive direction is up and the negative direction is down. So let's suppose that our object starts here at time t equals 0. So this is our starting position. All right. So that's where we start. And if we look at our graph, we can figure out, if we look at our graph, we can figure out what our initial velocity is. But we see that for a certain amount of time, our velocity is positive. So that means we're going to be traveling going up. So for a certain amount of time, we're going to be moving up. And then eventually we get to this point at time C where our velocity becomes 0. So we stop moving at that time. And what happens is after time C, we're no longer traveling up, we start moving down. So at time C, this might happen here, we kind of change directions and we start traveling downward. And so we travel downward for a bit, and then at time t equals d, that's the end of our interval, so we stop paying attention then. So at time t equals d, maybe this is our ending position. This is where we end up. So displacement is only measuring the distance between where we start and where we stop. So this is just this distance here. This is our displacement. Where did we end up? Where did we stop? And based on the graph, I think the net effect is, we traveled up for a bit and we moved down a little bit, but I think we're still the net effect there is we moved overall in the positive direction. Now what total distance is measuring is how far did we travel? So we have this distance here, which represents the distance in the positive direction. We have this distance here, which represents the distance in the negative direction. And so what total distance is doing is it's adding those two distances together. So usually what ends up happening, not always, but usually for an object that's moving back and forth, is the total distance it travels is going to be larger than its displacement. So if you're bouncing around back and forth, you're going to end up walking if you're pacing around, you've walked a whole bunch more than what your displacement indicates. All right, so let's try an example. Same graph, put some numbers on it. Let's suppose now that this graph here is modeling the velocity for a rocket that's fired vertically into the air. So its velocity at time t seconds after liftoff is this function -32t plus 160, and the units are feet per second. So in part A, we're going to find the displacement of our rocket during the time interval from 0 to 8. And so for displacement, over this time interval, all we need to do is we're going to integrate over that time interval. So we're going to look at all those tiny little changes to our position function over the interval from 0 to 8, and we're going to integrate our velocity. So that's what velocity is really measuring. It's just measuring all the little changes in your position at every single moment in time. And the integral says, well, let's put them all together and see what happens. See what the net effect is. So we're going to integrate from 0 to 8. Our velocity function is -32t plus 160 dt. Don't forget the differential at the end. Antiderivative, let's get the antiderivative of our function. So antiderivative of -32t is -16t squared. Antiderivative of 160 would be 160 times t. So our variable is t, that's why we're using t here. And then we're going to evaluate this from t equals 0 to t equals 8. Put our vertical line indicating that we're evaluating. And then we plug in. So top number goes in first. So we get -16 times 8 squared plus 160 times 8. So that's what happens when we plug the top number in, plug the bottom number in, plug 0 in, and we end up with 0 there. And if we do the arithmetic, what we end up with is 256, and our units are feet. And so what we've done essentially is we've looked at the area above the horizontal axis. We've looked at the area below. And we're looking at that net area. So this is the area above. Really, that's all we've done. Area below. And so we see after we've done this calculation, our displacement is positive. 256, positive 256 feet. So we've ended up moving up in the up direction overall. We went up for a bit, then we came back down, but we still had a net change in the positive direction over that time interval. And looking at the graph here, it makes sense that the value is positive, because if we look at that region for the area above, that region looks to be a bit bigger than that region where our graph goes below. So because that region that's above the x-axis or above the horizontal axis is bigger, the effect should be positive. We should have traveling in the positive direction. If those two regions were the same area, so if they looked about the same, well then our rocket went up, came back down, and hit the ground. So the net change would have been 0. All right, let's calculate total distance. So how are we going to calculate total distance? Well, we first need to, we're just going to calculate the area for each of those regions and add them together. And so the thing we need to calculate is, where exactly do we cross that horizontal axis? And that's what we want to find. We want to figure out our t-intercepts. So we take our velocity function, which is negative 32t plus 160. We set it equal to 0. So we're trying to figure out when our velocity is equal to 0, and then we solve for t. And if we do this, we get t is equal to 5. And that agrees with what we're seeing here on our graph. That's where we cross the horizontal axis. So after 5 seconds, all the fuel's exhausted and our rocket starts falling back. Well, no, our fuel probably got exhausted before that. But at that point, it starts falling back down to the ground. All right, so we figured out where the velocity parts is at negative. So do a little sign chart here. And we're only interested in our interval from 0 to 8. Plot where our velocity becomes 0. So at t equals 5, we're going to plot that point. So this gives us two kind of pieces of our interval. This gives us two subintervals. And if we look at our graph, in between 0 and 5, velocity is positive. So our velocity function is positive. The region is above the horizontal axis. And in between 5 and 8, velocity is negative. So the region is below the horizontal axis. So sometimes you might have to do a little bit of work here, but we can easily see this from the graph. So if you don't have a graph, you might use test numbers to fill in this sign chart. And then finally, we're going to go through and just calculate the area for each of those regions. So we have to split up. We have to break this apart and calculate each area separately. So let's look at that area above And really, we're saying area, the area under the curve there, but really what we're calculating, that area, that section that's above the horizontal axis, that really represents the distance traveled in the positive direction. So the area above really represents the distance that we're traveling in the positive direction. All right, so let's calculate it. So we're going to integrate from 0 to 5, and our velocity function is negative 32t plus 160, and then it's just a definite integral. So antiderivative, same one we calculated. So negative 16t squared plus 160t, and we evaluate from 0 to 5. And if we do the arithmetic there, we end up with, well, let's plug in negative 16 times 5 squared plus 160 times 5, which ends up being 400. So what happens from time 0 to time 5, we've traveled 400 feet in the positive direction. Now, at time 5, we stop traveling in the positive direction. We start falling back down. And so now we want to calculate the distance that we travel in the negative direction. And so the distance that we travel in the negative direction, that happens, we could think of it as calculating the area for this region, and that happens in between 5 and 8. So we're going to integrate from 5 to 8, our same velocity function. But now because that region is below the horizontal axis, in order to get the correct area calculation, we just have to make this integral negative. So the integral kind of tells you which side of the horizontal axis you're on. So if you do an integral and it's a negative value, it means more of your region is below. So integrating, just doing the integral from 5 to 8 is going to give us a negative value. So we have to just kind of introduce a second negative to calculate the area. We have to do a double negative, essentially. So because our region is below the horizontal axis there, to calculate that area, we're going to do the negative integral from 5 to 8. All right, so antiderivative, well, basically the same, just we have that extra negative in front. So a lot of your work you can still reuse. And then we're just going to plug in from 5 to 8. So the only difference there is this negative. And again, why we kind of artificially put that negative there is because the region is below the horizontal axis, so we have to negate it to get the area. All right, plug in. So we end up with negative, and I'm going to run out of room, so I'll leave this for you to fill out, but we end up with 144 here if we were to do that evaluation. All right, so we travel in the positive direction. That's 400 feet we travel up. Then we travel in the negative direction, so we start falling down. That's 144 feet. And so the total distance here that we travel is really the integral from 0 to 8 of the absolute value of our velocity function. But really what we're doing is we're calculating the area above, we're calculating the area below, and then we add them together. So area above is 400 plus area below is 144, and we end up with 544. So the total distance that we traveled during this time interval is 544 feet. So what was our displacement? Well, our displacement was 256 feet, and our total distance traveled was 544. So our rocket went a whole bunch, traveled a whole bunch more than what the displacement, our starting and our stopping values indicate. Let's try another one, just to see, get a little more practice doing these calculations. So let's say we have a particle now that's moving along a straight line, and its velocity at time t is given by t squared minus t minus 6, and our units here are going to be meters per second. Part A, let's find the displacement of this particle during the time interval from 1 to 4, and really this is not too bad. We don't really need to worry about where the velocity becomes 0 for displacement. So for displacement, we're just integrating our velocity function over our time interval. So velocity is describing all the little changes to our position over this time interval from 1 to 4. And so when we integrate from 1 to 4, it kind of puts all those tiny little changes together and says, this is what the end result is. This is what the net change in your position is. So our velocity function is t squared minus t minus 6. Let's get the antiderivative. So 1/3 t cubed minus 1/2 t squared minus 6t. Because we're doing a definite integral, we can leave off our plus c. Don't need to include it. If we were just doing an indefinite integral, that's where we need to include it in our calculations. So we have our antiderivative. We now need to evaluate. So the top number goes in first. So we get 1/3 times 4 cubed minus 1/2 times 4 squared minus 6 times 4. Then we subtract and we plug in our lower number. And it's just helpful to remember any power of 1 is 1. So we end up with 1/3 minus 1/2 minus 6. And if we do the arithmetic there, we end up with negative 9/2. All right, so let's just interpret this for a second. When we get displacement, there's kind of two pieces of it. There's the direction piece, and that's what we're seeing with this negative. So our particle is moving around. It's bouncing back and forth possibly. But what happened here is it started at some point, and then there's two ways it can travel. It can go in the positive direction or it can go in the negative direction. And what happens here is the net effect is that it moved ultimately it moved in the negative direction. So it might have went positive and then stopped and then came back. But in the end, it ended up to the left or in the negative direction from where we started. So that's what that negative represents. The net change is in the negative direction. And for our purposes, usually we're talking about left or right or up or down. So the negative direction is usually left or down. Not always, but usually that's what we mean by the negative direction. So what does that 9/2 represent? Well, that's just how many units. So this just means 9.5 meters. And I should say meters here because that's our units for distance. So we traveled, the net effect here is that we ended up 9.5 meters to the left of where we started. So just a reminder, displacement can be negative. That's okay. Where we run into trouble then is if we're trying to calculate total distance can't be negative. We can't have walked a negative distance. So distance is only measuring, how far we go. It's not keeping track of the direction that we go in. But displacement does keep track of direction. So now let's try and do the total distance for this particle. So we don't have a nice little graph here to help us along. So this will be, we kind of have to do more of the calculations ourselves in terms of finding where it crosses the horizontal axis, filling in our sign chart and all of that. So here we're going to be interested in the total distance during this same time interval from 1 to 4. And this ends up being the integral from 1 to 4 of the absolute value of our velocity. And so to integrate absolute value, we'll talk about this in a few minutes. The absolute value function, there's no nice antiderivative of it. So it's not something we can just find the antiderivative of. The way we work with the absolute value is we have to split the integral apart like we're going to do. And so to start with that, the first step is we have to figure out where our function crosses the horizontal axis. So we have to figure out the t-intercepts. So our velocity function is t squared minus t minus 6, and we set that equal to 0. Now here we can factor this nicely. So it does. It factors into t minus 3 times t plus 2. We figure out the t values then. So this one gives us t equal to 3. This one gives us t equal to negative 2. And then we go for our sign chart. And so we're looking at the time interval from 1 to 4, and we're only considering time values in between 1 and 4. So we found that our velocity function becomes 0 at t equals 3, but we also figured out that it becomes 0 at negative 2. Negative 2 is not inside our time interval here that we're interested in, so we can disregard that t-intercept. It's not in our interval. The only one we have to worry about is 3. So let's plot that on our sign chart. And so what we want to do now is figure out the sign of v on each of these intervals. So in between 1 and 3, what is the sign of our velocity? Are we traveling in the positive direction or are we traveling in the negative direction? And so, do the usual sign chart calculation, and maybe it helps with using a test number. So maybe you pick, maybe you pick like 1.5, something inside that interval, and you plug it into the velocity function. So when we plug it into the velocity function, and we've factored this, so it might be helpful to think of our velocity function in the factored version for our sign chart. When we plug a test number into the t minus 3 factor, that's a negative. And when we plug that test number into the t plus 2 factor, we get positive. So we have a negative times a positive, and the net effect there is velocity is negative on that interval from 1 to 3. Now we go to the second interval there, in between 3 and 4. Pick a test number. So maybe like 3.5. Maybe that one works out. Anything in between 3 and 4. And then go up to your factored version of the velocity function and see if you get a positive value or a negative value. So when we plug 3.5 into this first factor, we get 3.5 minus 3, which is positive. And then when we plug it into the second factor there, we get 3.5 plus 2, which is also positive. So positive times a positive, the result is positive. So what's happening on this interval is in between 1 and 3, our particle is moving to the left. And in between 3 and 4, our particle stops moving to the left and starts moving in the other direction. And so in order to calculate this total distance, we're going to calculate the distance that we travel in the negative direction. We're going to calculate the distance that we travel in the positive direction. And we're just going to add those two together. So distance that we travel in the negative direction is going to be the integral from 1 to 3 of our velocity function. But because we're going in the negative direction, we have to make this integral negative in order to get the distance. And then we're going to integrate from 3 to 4, our velocity function, to get the distance that we travel in the positive direction. And we don't have to change that integral at all because we're going in the positive direction, so we can just add that in. So the only adjustment here is when we're traveling in the negative direction, to get the distance, we have to negate that definite integral. All right. So now let's just fill in the pieces. And so this first part becomes the integral from 1 to 3 of t squared minus t minus 6 dt. The second part becomes the integral from 3 to 4 of t squared minus t minus 6 dt. And unfortunately, there's really no way to combine those two integrals together, back together, because the limits of integration are different, and the function that we're actually integrating, because of this negative, it's slightly different. So we can't combine these together into one integral, unfortunately. So we have to do them separately. Find the antiderivative. But the nice thing is a lot of the work is very similar. So very similar antiderivatives. Again, the only difference with that first one is there's a negative in front. And then we're going from 1 to 3. And we're going from 3 to 4 for this second part. So we just want to remember our vertical line for evaluate. Let's do the evaluation for that first part. And we get negative, what do we get? We get negative 9. So we're plugging 3 in first. So we get 27 divided by 3, which is 9, minus 9 over 2, minus 18. Then we plug the lower limit in, the 1, and subtract. So when we plug 1 in, all the powers of 1 are just 1. So we end up with 1/3 minus 1/2 minus 6. And don't forget about the negative that's in front there. And then let's evaluate that second part. And so for this, we end up with 1/3 4 times 4 cubed minus 1/2 times 4 squared minus 24. And then we subtract, we plug the lower limit in there. So we plug 3 in and subtract. So the nice thing, again, a lot of the work you can kind of reuse. So we've already seen what happens when we plug 3 in. So it's going to be the exact same thing. So when we did that first evaluation, we plugged 3 in, kept the negative out in front. We plugged the 3 in. We got 9 minus 9 over 2 minus 18. when we do the evaluation for that second integral, we're going to have the exact same thing. So we'll have 9 minus 9 halves minus 18. So a whole bunch of evaluating there. So when you do these, it might not be a bad idea to, you can kind of do them in parallel like this, or you might just do one integral and then separately, completely separately, do another integral and then just add the results at the end. In either case, when you do this, we end up with 61 over 6, which is approximately 10.17, and our units here are meters. And so when we do this, just a reminder, total distance is always positive. Well, always greater than or equal to 0. So a little bit of a way to check your work there. And the only way you can get 0 is if you're not moving. So the only way you can get a total distance of 0 is if your velocity function is just constantly 0. So if you see any variables in your velocity function, you should end up with a positive total distance. All right, so let's just look at, so this is a very subtle point when we're integrating absolute value. Why do we need to break up the integral when we have that absolute value? And the reason is because absolute value is a piecewise function. And so when we integrate a piecewise function, we have to split up our integral based on where those pieces happen. So absolute value function is a piecewise defined function. And we actually looked at an example of this last time where we did the area under a piecewise function. Kind of was like a triangular region and then a rectangular region. And the way we did it with integrals is we had to first do the integral for the triangular region, then we had to do the integral for our rectangular region, and then once we had those two values, we added them together. So for piecewise functions, you have to split up the integral based on the pieces of your function. So specifically for absolute value, so let's look at the absolute value of v of t. It's defined differently. It's defined to be v of t if velocity is greater than or equal to 0. And this is true for any absolute value. It's equal to what's inside if what's inside is positive or 0. And it's equal to the negative if what's inside is negative. So this is how we define absolute value. So what was our sign chart for this particular velocity function? Well, we had the interval from 1 to 4. We plotted 3, and then we found that velocity was negative on this interval and positive on this interval. So when velocity is negative, the absolute value function is defined a little bit differently. So essentially what we found is that the absolute value of the velocity in this case is defined to be the velocity function. Everything was fine in that interval from 3 to 4. We didn't have to adjust our integral at all. But in that interval from 1 to 3, that's where the absolute value function changes our definition here. So it would become in that interval from 1 to 3, the velocity, the absolute value of our velocity function would be equal to the negative velocity. So it's what the absolute value is doing is it's kind of like a double negative. And so that's why we had to throw in that extra negative into our integral there for that distance that we're traveling in the negative direction. So really behind the scenes here is to get the total distance, we're doing the integral from 1 to 4 of our absolute value of our velocity function. And we break apart that integral. So we look at the different pieces of our piecewise function. So the first piece was from 1 to 3. So we integrate from 1 to 3. That was one piece of our function. And then the other piece was from 3 to 4. And once we've kind of split apart our integral like that based on where our piecewise function breaks apart, then we look at, okay, well, actually, what is the absolute value of v of t on that first interval? Well, it's negative the integral from, and let's keep it inside. It'll be the integral from 1 to 3. And what is the definition of absolute value v of t on that interval from 1 to 3? Well, it's negative v of t. And then on the interval from 3 to 4, what is the definition of the absolute value of v of t? So what is the definition of absolute value of v of t in between 3 and 4? So we go to our piecewise function, find the interval 3 to 4 in our definition there, and then we just read over and we see that it's just our velocity function. So it's a really subtle point here when we're trying to integrate the absolute value function. We really have to break apart our integral based on where the function inside that absolute value sign becomes positive and where it becomes negative. And so we can see here why we end up with that negative is really from the absolute value function. We end up with that extra negative there when our velocity function becomes negative. All right, so I think we'll stop there for today. So that kind of looks at one last application of definite integrals in the context of motion in a straight line and net change. And when you get into Calc 2 in the spring, if you're taking it in the spring, these are two good sections, this motion in a straight line and the area one that we just looked at last time, because we're gonna be talking about area under the curve or area between curves. So you're going to be doing very similar calculations to what we're doing here in 142. So this might be a good couple sections to revisit once the spring semester starts back up. All right, so we'll stop there for today. Next time we're going to get into the kind of the definition of definite integral. So we're going to see how, really what we're doing when we're integrating a function. And it's, we're going to see that it's pretty difficult to do, actually. So what we've been doing so far, this is the easy way to calculate a definite integral. What we'll see next time is they're actually very difficult to calculate directly. But we'll get to that next time. Reminder, you'll be getting your graded exam back sometime later today. Go to recitation, and if you have any concerns about how to do a problem, go to recitation and TA will go over the exam questions. We have our follow-up exam 6 on Thursday. So that'll have questions from exams 1 through 6. So make sure you know which ones you need to redo. You by no means have to do all of them. You only have to do the ones that you haven't gotten the first time. I have office hours tomorrow. If you want to go over any homework questions or questions on your exams, feel free to stop by. All right, so good luck with all your other classes, and we'll see everyone on Thursday. Bye-bye.